Hi guys, thanks again for your flexibility in watching this video at home. Again, in AP, you'll do a lot of this type of thing, so it's really important that as you're watching the video, you rewind and stop and pause and write things down, make better notes for yourself, re-listen to things, whatever you need to do to make sure that you're understanding. We're not going to do the entire notes paper you have in front of you. We're only going to do the first two of the three concepts that are on there. The other one we'll do in class together. But what's most important for me to explain to start with this lesson is about a concept called equilibrium. Le Chatelier's principle is something that fits into the concept of equilibrium. And we're not going to get deep into equilibrium, but it's important for you to understand what that term equilibrium means, because a lot of people have the misconception that equilibrium just means equal, and that's going to cause you a problem if that's the case. I need you to fully understand what's actually happening. Now, to do that, I'm going to need you to step out of your box a little bit, because your experience with chemistry so far has been reactants make products. You know, you take your reactants, you mix them together, and they form products, and that's the end of the story. But there are so many reactions out there where at the end of the reaction, what we call the end of the reaction, which by the way is called equilibrium, at the end of the reaction, there's not all product and no reactant left. In fact, a lot of reactions end up at a point where there's a significant amount of reactant still in the container, a significant amount of product in the container, and yet if you're measuring their concentrations, nothing's changing. And that point is something called equilibrium. So again, I need you to kind of take out of your mind that reactants make products and that's all that happens, because what's really going to happen in a reaction is this. The reaction's going to start. The reactants are going to react, and they are going to start to form product. And at the beginning of a reaction, that's the predominant thing that's happening. Reactants are colliding and making product. But eventually, you'll get enough product built up in the container, and that product will start to reform the reactants. So undo itself, essentially. And eventually, you will reach a point where the reactants will be making products, and the products will be undoing back into the reactants at the same rate. That is the point of equilibrium, and that's why it's called equilibrium, because they're doing their thing on each side of the reaction at the same rate. And so we don't see a change in either one of them, their concentrations. This concept is difficult to understand because you can't really see it happening. But the best way, I'm going to kind of use an analogy while we're talking about this equilibrium. I'm going to use the analogy of a seesaw. Let's say you walked over to a seesaw. You know, when you sit down on a seesaw, you level it out, right? So it's flat. You're sitting there waiting for somebody to come up, and a sumo wrestler comes up, and he sits on the end of the seesaw, and immediately the seesaw has to figure out where its balance is. So as soon as he sits down, there's some bumping around. We've all been on a seesaw and felt that. You feel that bumping around, and then all of a sudden it stops, and you are at what you'll call the equilibrium of the seesaw. Well, if you're with a sumo wrestler, say you're the reactant, okay, the sumo wrestler is the product, there's a lot more of him than you. So the balance lies towards his side and the product side. So there's more product than reactant, but you're still there. There's still some reactant there. Then let's say you're on the seesaw again, it's flat, nobody's on the other end, and a little 2-year-old comes over and wants to seesaw with you. They get on this other end of the seesaw, and again, there's that jolting effect. Everybody's kind of equaling out. That's it reacting. And then all of a sudden, there's more of you than him or her, whoever the 2-year-old is. You outweigh that 2-year-old. In that case, you'd have an equilibrium where there was more reactants than products in your container at equilibrium. Or again, seesaw, you're flat. You and your clone comes and hops on the other end. At first it kind of teeters a little bit, but then it evens out exactly the same because you obviously weigh the exact same as your clone. In that case, that would be equal amounts of reactant and product. But you can tell from our example that it didn't have to be equal amounts. What had to equal was the leveling off. It just had to level off somewhere. Either a lot of reactant and a little product, a little reactant and a lot of product, or some amount of each one. and equilibrium can be anywhere between those. And that's really the concept. So let's get into your notes a little bit. We'll revisit these ideas here in your notes, because in your notes we kind of go over the same thing. These reactions that I'm referring to are called reversible reactions. And as you can see from our example, I was telling you reactants not only become products, but products actually become reactants. And so you can see that the definition of a reversible reaction is a reaction in which the products can rearrange and regenerate the reactants. Okay, and the reactions can be going in the forward direction to the right, like the yellow arrow is showing, or in the reverse direction, like the pink arrow. Notice in equilibrium problems, we use that double-sided arrow. We'd seen that before, right, with weak acids and weak bases, and they are definitely an equilibrium situation. So that's a good thing to think about. You know, we said with weak acids, they don't completely break up. So you're going to have an equilibrium between what was your original molecule and the broken up version of that. So that's what that double-sided arrow is showing you. Okay, and then again, we said the definition of equilibrium is when the rate in the forward direction is equal to the rate in the reverse direction. So it's not equal amounts of reactants and products, it's equal rate of formation of reactants and equal rate of formation of products. So the concentrations aren't changing, essentially. Okay, so that's the concept of equilibrium. Now, the reason why that's important is because that is going to then allow us to discuss Le Chatelier's principle. So you have this reaction, it starts off, it gets to equilibrium. All reactions go to equilibrium, every single one of them. So it goes to equilibrium. Once you're at equilibrium, it wants to be there. That's its like pinnacle, that's its best point it could be at, is at equilibrium. Well, if we come along and we do something to that equilibrium and we mess up that equilibrium, Le Chatelier's principle says that the system is going to shift in order to reestablish its equilibrium. And what I mean by shift is it's either going to make more reactants or make more products to get back to equilibrium. Now, we're not going to get into the math of this, but just so that you have kind of an idea, this is hard for me to write with. Whoa, hello. It's hard for me to write, but equilibrium is essentially, is essentially determined by taking the products and dividing them by the reactants. That's the math part of it. And again, we're not going to get into that, but it's going to help you think and kind of have the idea of what the math looks like and how we are going to reestablish the same ratio we had before of products over reactants. Okay, so here are the changes we're going to do. This is the ways we're going to screw up this equilibrium. Sometimes we call them stresses. This is how we're going to stress our system out. We're going to cover two of them in this video, and then we'll cover the other one, the temperature one, later. So the first one is changing the concentration of a reactant or product is going to screw up equilibrium. So let's say we're at equilibrium. We come along and everything's hunky-dory, and then all of a sudden, so you're on your seesaw. Let's use our seesaw example. You're on your seesaw, everything is hunky-dory and wonderful, and then all of a sudden somebody else comes and sits on the seesaw along with the sumo wrestler. That's going to screw up your equilibrium, and the system wants to get back to where it was before. So it's going to shift in order to deal with that. Now, I call this common sense. But I don't want to say that in a rude way, because it is something you have to think about. But if you think about this from a logical point of view, it makes a lot of sense. Okay, so if this one says if you add more of a reactant or product, the system will shift to consume or use up that added substance. So let's say you had a system at equilibrium, everything is great, and all of a sudden you come in, you shove in extra reactant. The system has to get its balance back. So if you shove in extra reactant, it's going to take that reactant and turn it into product, some of it, in order to reestablish the same ratio of reactant to product it had before. Okay, it's about reestablishing the ratio. So I call this common sense, because if you have too much of something, you're going to use it up. Okay, you have too much of something, you're going to use it up. Let's say your mom goes to the grocery store and tuna's on sale. I don't know if tuna's the best example. Let's use something yummy. Hostess cupcakes are on sale, and you have 14 boxes of Hostess cupcakes in your house. All of a sudden, you're going to see Hostess cupcakes all the time. Okay, your mom's going to be making desserts with them. You're going to be having them in your lunch. You have to consume them if you have too much of something in order to reestablish your equilibrium. Okay, now the same goes if you take it away. If you don't have enough of something, the system's going to shift to reproduce it. Okay, so if you really like Hostess cupcakes and there are none in your pantry, you're going to go buy some. You need to reproduce them in your pantry so that you have them to eat. Okay, so that's why I call it common sense, is it makes sense. If you have too much of something, you're going to consume it or use it up. If you have too little of something, you're going to want to reproduce it. And the way that we do that is by discussing a shift. It's either going to shift to the right and make more product, or it's going to shift to the left and make more reactant. And that's what you need to be thinking about while you're doing these problems. Now I want to show you how the problems work. It'll make hopefully a little more sense to you as you're looking at the actual problems. This first one is very generic. So A makes B, okay, very straightforward. And so the problem says, and again, the double-sided arrows are equilibrium. The problem says we added more A. Okay, and they want to know which direction this reaction is going to shift to reestablish its equilibrium. So if the issue is that we have too much A, we have too much A in our container, the reaction is going to shift to make more B. By doing that, it uses up this A, gets more B, and that ratio, products over reactants, goes back to equilibrium. And that's the point of it. It wants to reestablish its equilibrium. So the answer to this question is that it will shift to the right. Oops, sorry about my little notes here. It'll shift to the right in order to re-achieve the balance. Okay, shift to the right in order to re-achieve the balance. Okay, and again, that's to use up that additional A. All right, let's look at another example. This one's got a lot more things in it, but it's still the same idea. We have 2 A's and B making 3 C's and D. It tells you we're removing some of D. So the problem is we don't have enough D. Okay, so this reaction needs to make more D. It's going to shift and take 2 A's and B. It's going to make more C as well, and that's okay, because the point is we need to get more D. It's okay to have more C, but we definitely need more D. So if you take away D, this reaction is going to shift to the right in order to replace the D that you removed. Okay, so again, common sense thought, if there's not enough D, we need to make more. So it'll shift to the right. You could also say it shifts forward. You could say it's going to produce more D. It's going to go towards the product side. There's a lot of different ways to state it. But the point is, whatever you say has to infer that D is being increased, that you're going to then try to re-increase it because you removed it. Okay, so that's the idea of concentration. Now, pressure is the second stress, and pressure actually only applies to gas phase reactions, but you don't have to worry that I'm going to try to trick you or anything. Everything I give you will be gas phase, and it actually is almost the same. Okay, it's the same concept as concentration. If there's too much of something, you need to consume it. If there's too little of something, you need to get rid of it. I'm sorry, if there's too little of something, you need to replace it. So same thing with the pressure, but we're going to have to look at it in a little different perspective, because you can't just look at the equation and tell from the reactant side and product side what's happening with the pressure. There's a little bit more that we have to look at. So let's start with the general rules, and again, you'll see they're very similar to the ones we just did. So if the problem is that you've increased the pressure, so maybe you change the volume of the container, put it in a smaller container or something, the system has to shift to decrease that pressure. So if the pressure's too high, the system doesn't like that. That makes it out of whack. And if it's out of whack, it wants to decrease and go back to having its right balance that it had. So if the pressure's too high, it wants to make it lower. If the pressure's too low, it's not where it was before, it's now lower than it was before, it wants to get back higher. Okay, so again, same concept. It's going to fix whatever stress you put on it. Now here's how we decide this. Here's an example. It says 2A yields B. And it says if you increase the pressure of this system, which way will it shift? First of all, when it says increase the pressure of this system, it means everything that's in the container, which is whatever balance it has between its A's and B's. So in this container, you have both. This change is happening to the entire container. Sometimes people think, well, we're increasing the pressure of A, and so what's going to happen to B? No. A and B are in this container together. We are changing the pressure in the container. So the system itself is going to go, how can I fix this? If the pressure's too high, I need to bring the pressure back down. But it has to do it within this actual reaction, okay? So how does that happen? Well, if you take a look at these coefficients, they're going to be your key to pressure. If you notice on the reactant side, there's 2 A's, and on the product side, there's 1 B. So in other words, 2 A's are coming together and making 1 B molecule, okay? If you think about numbers of particles, there's going to be 2 moles of A for every 1 mole of B. Think about what is going to create more pressure. Will it be 2 particles or 1 particle? Hopefully you said 2 particles creates more pressure. If that doesn't seem logical to you, then think about like Disneyland on a crowded day where there's lots of people, lots of moles of people, versus a not crowded day when there's not a lot of people. Okay, you know that there's a lot more pressure exerted, people bumping into each other when there's 2 of something as opposed to 1. So if the pressure is too high, the system needs to bring the pressure back down. So it's going to shift towards the B side, because on the B side there's fewer moles of particles. So you can see the answer says it wants to decrease the pressure, so it'll shift to the side with fewer number of moles. Since less moles exert less pressure, this reaction is going to shift to the right. So it's going to shift to the right to decrease the moles. So when you've increased pressure, you want to decrease moles. That's how you're going to decrease the pressure. Okay? Obviously, the opposite is true as well. Let's take a look at one more example. So here's our bigger equation. Lots of things going on here, but if it's about pressure, which we see it is, it says in the above reaction it experiences a decrease in pressure. As soon as you see it's about pressure, total your moles. On this side I have 3 moles. On this side I have 4 moles. So 3 moles, 4 moles. Again, this container has whatever balance it has. The problem is there is too little pressure. I need more pressure. So it's going to shift to the side with more moles of gas, because that will bring that pressure back up. So the answer to this one is that it will shift to the right to increase the moles of gas and therefore increase the pressure. So those are your ideas. And again, think about it from a common sense point of view. It needs to fix the problem. If the problem is too much of something, it's going to decrease it. If the problem is too little of something, it's going to replace it. Okay, and we will try some problems with this so that you can get comfortable with it. And we'll discuss temperature, of course.